Welcome. Thanks for coming. We're going to be covering some work that we're doing between AWS and Volkswagen. I'm giving a brief introduction to how we're jointly transforming automotive manufacturing and what we're doing with a project called the Digital Production Platform. I'm here with my colleague, Uwe Wieland, so maybe I'll let you introduce yourself.
Hello together. Also from my side, a warm welcome to our presentation. It is an honor for me to give our first insights into our daily work at our common digital production platform and to explain the platform development from a more technical manner based on the real-world example DSFM Plus. Representing our great team, there's Matthias and Paul in the back who implemented the solution. I'm allowed to guide you through this presentation. My name is Uwe Wieland, and I'm a software development manager at VW. I'm since October last year working for Volkswagen, and I have some experiences in production systems and Six Sigma, and we hope you enjoy our presentation.
Great. Yeah, my name is Pascal Hahn. I'm managing the development and the product side for DPP on the AWS side. DPP is it's a digital production platform, and what that actually means is that we're working on optimizing processes in production and logistics. So this, Uwe is going to give us a bit of an overview on what are the actual problems in manufacturing and logistics that we're solving. Then we're going to go a bit through how do you actually start building a platform like this. Like we know what we want to achieve, we want to optimize production, but when you start on a journey of this scale, it's actually not that easy to figure out where do you start. So we took an approach that we started with use cases and then derived the platform from that, so we'll explain that a little bit. And then we're going to do a deep dive into DSFM Plus, which stands for a Digital Shop Floor Management System. Uwe's going to describe a bit what is this that we're actually building there, how is it structured, and then do a deep dive on the architecture on what does something like this actually look like. All the way from the machine to a cloud-based web application. And then we're going to show a high-level target architecture of the platform that we developed by doing multiple use cases on it, and then kind of learn what components do we actually need. With that.
Okay. Referring to the presentation from Sarah Cooper and Uli Petri yesterday on the strategic approach on digitalization and automotive manufacturing, I would like to give you a brief insight into the current challenges and goals that Volkswagen is pursuing with the industrial cloud and the technical platform DPP. In summary, the industrial cloud and in special the technical platform DPP is an enabler of VW Digitalization initiative to achieve the set of operational excellence goals over a 5-year horizon. In order to achieve a performance increase of 30%, it is necessary to optimize the entire value chain holistically, not only on the optimization of individual plants and processes must be addressed, but also their effects on upstream and downstream processes. For example, to achieve cost saving, error prediction, or avoiding process losses, it is necessary to obtain transparency about the current processes and the involved equipment. If we met this challenge for the different circumstances, e.g. regional process differences or heterogeneous equipment, we can use intelligent technologies for advanced root cause analysis of process losses and drive automated improvement mechanisms such as sustainable monitoring of the improved process. Through this approach, human activity will be supported by data-driven decisions, and a new maturity level in automation of processes will be achieved.
Okay. So, figuring out what the platform looks like, we started in the beginning of the year. The target that we're having from a business perspective is, as I said, to optimize production. So how do you do that? We're using a lot of AWS services today, and the count is growing as we speak pretty much. We're heavy users of IoT Sitewise, and are also going to show a few architectures around that service to really start managing your machine data. Like, it all starts with the data you need to get from the machine somehow. In our case, we're going to look at the architecture in a bit more depth, but you really try to get data calculated, like your overall equipment efficiency. So how well is equipment running? Like, if this machine can produce 1,000 doors an hour, how many do I actually produce right now, and then how many am I not producing and why? Where Uwe is going to give a bit of an insight later. The platform itself is a microservice-based architecture where we have the AWS services as one part of the architecture, but then we're augmenting it by building new services jointly. So when we started this year, the first problem we had to solve was how do we actually get our developers enabled? Like, Volkswagen has internal tools, Amazon has internal tools, but we're collaborating. So what does it take to actually get your developers going? So we built a web-based application and a backend that can help us to manage something called landing zones. So your Amazon accounts with connectivity, like permission setups, integration with security systems, and so on and so forth. Then we kept going. It's like, okay, we need OEE numbers, as said, like the operational equipment efficiencies, effectiveness. We need that. So how do you generically calculate something like this? What does it actually take? And we're gonna show briefly how we actually do that. There's a lot more services we're developing at the moment that are not on here yet because they don't yet exist, unfortunately. But it really, the intent is to augment the AWS offering with new services that are very specific to problems we're having together with Volkswagen. For that, there's a lot of different data we need to get from machines into the cloud and then back onto the shop floor to basically drive these applications across 102 or roughly 102 plants that Volkswagen is running globally. In the fullness of time, the idea is to take this architecture and apply it more broadly. So a lot of the problems that Volkswagen is having to solve in manufacturing are actually not unique to Volkswagen, but are manufacturing problems in general. So the intent is to open up this platform in a more broad fashion and basically use the initial DPP service as a bootstrap to this broader picture. When we started out to build this platform, it was interesting. Uwe has a lot of experience in manufacturing. I actually don't. So we spent a lot of time in the factories. We talked to a lot of people, and we learned a ton. And you start looking at machinery that is not something that a software engineer works with on a daily basis. So you sit down and you talk to the operators and they start explaining. It's like, well, this is how a CNC machine works, or this is how a metal press actually works, and this is where things fail when you try to build a door. And those are problems that, like, it's a physical problem and a machine problem. So for a software engineer, it was very important to actually try to understand as best as we can the aspect of production, to then look at, okay, so AWS has a ton of different services. So what can we actually use to solve some of these problems, and which of these problems make sense to be solved in software? So we talked to plant managers and operators and supervisors and like the planning folks at Volkswagen a lot to really try to understand what problems do you actually have and which problems matter to you, and where do we start? By doing so, we decided to take an approach to build this platform by not starting with the platform. So we looked at use cases that bring a lot of value to Volkswagen and identified actually amongst the DSFM Plus use case that we're going to dive into a bit deeper, several others that really mattered a lot and gave us the opportunity to actually learn how to do this right. So identifying the use case that matters to you is a great approach to get going. Like, make sure it actually counts for your business when you solve the use case. From there, we started implementing it without any platform, or I think without any platform is maybe an understatement, because you have the AWS platform that we used to deliver this first use case, but there were no custom components in the end when we built it. So AWS has a lot of services on the shelf where you can do this. But to start accelerating your development and to deliver a whole ecosystem, the next step we did was look at common problems that we solve in every use case and that are hard and that take a lot of time or have a high amount of complexity. When we identified a few of those, we started looking at components. So as I said, like, we figured out that, hey, it takes us like weeks to get an account for a developer to get moving. And then getting that set up in a consistent way and managed in a secure way was a huge investment. So let's figure out how we can solve that problem. Then the next one was, okay, we have a lot of machine metrics that we need to manage. We need to calculate them somehow. So what does an architecture look like to do this? How can we help accelerate that? Once we identified the component, we started to deliver them. So we started bootstrapping teams around it. We're using AWS ways of working in this case, so something called pizza teams, which I'm not sure if they mentioned it in other talks, where you basically build a team around a domain and you let them run free and deliver that on top of AWS. They started delivering the first platform components, but then you actually need to make sure that they deliver on the premise and on the expectations you had. So let's move use cases over to that component. Let's actually use those components actively and learn what works with them and what doesn't. Once you figure that out, you go back to step one. Either you keep iterating on your component, or you figure out that, hey, there's another one. Let's do another use case, and you do this over and over and over. The result of this is that over time, your platform gets richer and richer, and you actually ensure continually that whatever you build is actually aligned to the problem that you're trying to solve, which especially in the DPP case, there's so many areas where we can optimize that figuring out where to start is non-trivial. So with that, I'll give it back to Uwe to take us a bit deeper into what we actually built.
Okay, so let's dive deeper into our use case, digital shop floor management, short DSFM+. Our vision is to establish a group-wide digital shop floor management system for our brand component technology at first, to continuously improve the processes on the shop floor. Therefore, we want to use our established group production system with all entire tools and processes on a new digital level to provide processes integrated transparency on a detailed machine level and on an aggregated view over lines and over plants. Built up on this, we are able to spend more time for problem solving and sustainable improvements of the machine availability, optimizing throughput times, and increasing quality. At the moment, there is more or less analog information process in place to control and improve the shop floor activities and processes on a different level. The well-defined information cascade you see here works well in a day-to-day business, but has some limitations and efforts. For example, gathering information to determine the current performance status is characterized by many manual activities and is not very up-to-date. It's only for day-by-day basis. Often problems can only be detected and analyzed with a time lag, which leads to efficiency losses. Furthermore, the approach is very reactive and not more or less proactive. With the new solution, we want to bring the information to all stakeholders in a timely and on-demand manner. On the one hand, we enable a timely identification of problems and support the reactive problem-solving process with up-to-date information, and on the other hand, we create the conditions for proactive and automated error detection procedures. What does the described approach look like from a conceptual point of view? In each factory, we have a discrete manufacturing process that manufactures a product such as a cylinder head for an engine in manual and automated process steps. The machines in each process step are controlled by one single production logic controller, short PLC. Furthermore, employees interact with different IT systems and with the machines during the processing of the product to control or configure something. So we have a lot of different data sources which holistically represent a data image of the whole process. In order to recognize process problems fast and to take action, this data must be presented up to date, in detail and completely at the effective process step. Here, it is called Team Tafel, which is a performance view in a very actual manner. Furthermore, we need a long or mid-time indicator to assess the process capability. In an easy way explained, we will see on a shift base, have we produced the right number of parts in the right, correct quality with the best possible use of our resources. Here it is called overall equipment efficiency. Later in the presentation, I will explain on a concrete example the OEE a little bit deeper. Okay, to realize this solution, we implemented the following modules and components and the necessary technical capabilities on the digital platform, production platform in the first MVP in the year 2019. In addition to the visualization of the OEE and the machine states, it was necessary to build a component for the manual data enrichment because that we are able to calculate the right measures for the OEE and to provide valuable information about the cause of the problem. So we look with the semi-automated loss recognition, especially on the reasons for the problems, the 20% of the OEE we want to reach. Another special feature for the OEE calculation is the shift calendar on the left side. It is necessary also for calculating OEE in the right and comparable time interval because we have fixed intervals for a shift, but it differs from plant to plant, but the duration of the shift is 8 hours, and so we must implement a separate time scheduling for this because site-wise at the moment they are not implemented. Okay. Let's go a little bit deeper in the technical architecture. For the implementation of the application, the architecture below shows the AWS services used on an associated technical capabilities. Along this architecture, I will guide you in the next few minutes and show you selected points of our technical realization and share you our first experiences. For us, IoT Sidewise here in version 1 plays a key role for technical capabilities like data storage, metrics and KPI calculation, and data structuring. In addition, we offer our first UI, which allows adjustments and extensions without programming background for our engineers. Here I can highlight that Volkswagen can achieve a high scaling effect in operations through such a managed service like Sidewise in version 1. Starting with the data integration, I will show you two different approaches regarding to our existing heterogeneous situations on the shop floor in two different plants. At first, you see our preferred way for machine data integration based on our actual target architecture. In the scenario, each production line is controlled by one PLC. Each production logic controller represents one data source in our scenario. Furthermore, you see here one industrial edge gateway in place which have different tasks. At first, it works as an OT/IT gateway to integrate different industrial protocols like Modbus and RFC 1006. Second, it realizes the data transformation and the mapping to OPC UA. So it acts as an OPC UA server. The next component in place is our edge gateway, which is running on a virtual machine on-premise. It consists on AWS Greengrass, running the AWS IoT Sidewise connector with two Lambda functions at the moment. One puller function and one pusher function. The puller function represents the OPC UA client, and the pusher function sends the data to the enterprise cloud IoT Sidewise. At the moment, there is no further functionality for data enrichment or aggregation, for example, on the edge gateway in place. but we must work on this, for example, to reduce data volumes and to annotate measure values with more semantic. For example, we have a value from the PLC, and you have an ID, and we need the real name of the machine or some configuration parameters from our existing systems, and so we try to join this on the edge gateway in future. The advantage of this architecture is that we are not directly accessing the PLC to save resources on the PLC when several systems requires the same data from this PLC. The effort of the data replication is therefore not on the PLC, but on the industrial edge gateway, which prevents influencing the operational process. In the second plant, we find another typical picture of a brownfield scenario. Instead of the industrial edge gateway, an existing SCADA system represents the functionality for data ingest from the PLC, such as a storage layer for the machine data. In addition, the existing systems have also capabilities to control the process in a supervisor role, which is representing another maturity level of process control, like in the first scenario. Furthermore, you see here our own custom connector with an OPC UA endpoint to realize the same capabilities relating to the first scenario. But this solution is not our way we want to go in the future, because there are a lot of pitfalls and efforts. Our preferred solution is an DB connector for Sidewise to integrate such scenarios in future. So we can take a little bit more in detail. On the next slide, we have additional individual components that makes the data integration process more error-prone and increase the day-by-day operational effort at the moment. Due to the process control function of the SCADA system, we have a high resolution of data points for the relational database. However, this resolution of data cannot be easily transported via OPC UA and must therefore be preceded by a transformation, for example, reduce the information about the state changes over time. If there was the possibility to query the data without an OPC UA directly via Sidewise, a more stable process could be established. We looked at how we integrated the machine data in different brownfield scenarios via IoT Sidewise. At this point, I would mention that we are driving a complete serverless approach to keep VW operating costs to a minimum. The basis on this cloud-native development is that we build our solution directly on AWS infrastructure and higher value-added services, and avoid in such case the whole operational management and the relating effort for updating, patching, and maintaining the compute or network infrastructure and operating systems. Furthermore, we built all this, what you see here, as infrastructure as a code on a high automation level, so that we have no manual processes in this architecture at the moment. Also, you see here the integration of the VW identity provider via AWS Cognito as a first reusable component for further use cases. So like Pascal mentioned, we become increased case by case our functionalities in the platform, and here's the identity provider matching is the first component we can use in the next or further use cases. Now we have look on what we do in the integrated data to establish a demand-oriented solution which will help our different stakeholders to achieve operational excellence. In the last minutes, I have explained how the technical data flow from machine to cloud works, but that's not all. We need a logically representation of the physical asset and their structure in place before the complete data integration works. Furthermore, we need the asset structure for analytical considerations. For example, to perform a calculation, not only the asset level, we need the hierarchies between assets for aggregation on a line basis and on a plant level. In addition to the initial creation of the assets, we need the ability to update these structures or to delete this if necessary. Here you see our MVP-based asset structure from one plant. It consists of 94 automatically imported assets via a custom resource for IoT Sidewise. It looks very funny at the moment here. You see the graph on the right side. But you see here the way we learn together with AWS on a very pictorial example. So in this case, Sidewise need also other visualizations of asset structures to become more usability for our engineering stakeholders. But nevertheless, I will show you a way how we integrated and updated different asset structures from different plants in an automatically manner by using AWS technologies. To make this happen, we use a custom cloud formation resource called custom resource. Through this approach, assets, asset structures, metrics, and the mapping of raw values to measurements are created, updated, and deleted automatically. For this way, we have stored a separate config for each plant in a S3 bucket. In a first step, we load the relevant config and validate them in a second step. Validation on this point is very important to ensure the correct execution of the entire transaction to avoid data misalignments. The response, of course, can be successful or not, and it's stored in another S3 bucket and waiting for the execution stack to arrive. Here, it should be noted that this bucket is currently public. Therefore, we must take care that no stack traces or insights should be saved in this. So the advice is to use only simple messages like success or failure without any further content. The following slide shows you the concrete procedure as code. A first event is triggered by CloudFormation. The request type is set by CloudFront. The internal validation takes place, and it validates if the right variables are in place. After that, the config is fetched from the S3 bucket with the asset model information, and our config validator will check the config syntactically. So we check the JSON file where the config is stored in. The execute request use components from the Sidewise SDK and execute the request depending on the request type and the submitted config. If the assets with the characteristics and structures have been created, we can start calculation KPIs. Here you see a section of an asset template in JSON, which is part of the config I told you before. In this example, you see the calculation of the KPI OEE for a 15-minute time interval. In detail, it is the calculation of the value-added availability of one machine. For this calculation, you need different metrics which will be calculated by real measurements from the asset. First, you need the metric target cycle time from the machine. This is represented as a constant value with the variable var underlined time. The second metric is the part I/O, represents all successful produced parts in the defined interval of 15 minutes. Last but not least, the metric running time is calculated by value-added time minus wasted time or failure time. To give you an example for the OEE calculation, you have a target cycle time of 1 minute and you produce 12 goods good parts by having a 40-minute running time in the 15-minute interval. You will have an OEE in this case from closer to 86%. On the next slide, I will show you the technical way how we make the actual near real-time and historical data accessible to our user. I think it's a standard way to get data to a front end in AWS. Therefore, we use two ways. Over an API gateway as a single central access point for our AWS Lambdas. So we have one entry point to our backend service with an integrated authentication. In detail, we have one way for near real-time values, which is implemented as a PubSub mechanism based on WebSockets. And we have a REST API for the historical values, but honestly, the path with the PubSub is still implemented based on Sidewise version 2 SDK documentation, but there is no proof with the service for Sidewise at the moment, so we hope to do this in the next few weeks. At last, you see the result. Our single-page applications, we have more single-page applications, but you see here one. And you see, for example, the status of the machine, which is such a case for the live API path. And you see the availability of the machines over time, which realized with the REST API way. As you see the histogram on the right side, which is filled by the REST API call. In this project, we have designed and implemented a lot of visualizations for the shop floor management. With the availability of Sidewise Monitor, we will prove the replace of some visualizations by the Sidewise Monitor. Yes. So, Pascal, I will take it to you.
Through the architecture of DSFM Plus, but I'm going to give a brief overview of what the platform architecture currently looks like after we did a few use cases on this. We're structuring the architecture along various tiers that help us to kind of structure our thinking on what capabilities do you actually need at what point of an entire platform that really needs to span all the way from a highly constrained environment that is right next to your machine all the way to the public cloud. I'm going to do this in a bottoms-up fashion. It's a bit easier to think about that way. At the shop floor, the amount of computational devices we're having is fairly restricted. And the main purpose you really have is how do I get my machine, how do I get my machine data out of the machine? So Uwe was talking earlier that we have these OT/IT gateways that help us to translate data from a source protocol, which very often is a field bus protocol that connects your machine, to something that is IT compatible, such as OPC UA and MQTT. We have a multitude of gateways in action here. Those are usually deployed very, very close to the machine. The amount of computational power you have in those is also relatively restricted, generally. From there, because it is a highly constrained environment that these gateways run in, so be that on the networking side as well as what you can actually do on the physical side, we have something called the edge tier. So in the edge tier, this is usually a compute room somewhere in your plant, or in a large plant, you might have a small data center or a mid-sized data center that is close in proximity where you basically have compute capacity. On these edge gateways, the main purpose is that we want to start aggregating data from multiple OT/IT gateways and start calculating metrics. We want to enrich the data with a few data sources, as Uwe was saying, and then really load it toward the public cloud. The other services we're providing on these gateways are actually services that help us run the OT/IT gateways. So this is simple things like they need DNS, they need a NTP server, so you preferably have the same time across all the gateways you ingest your data from, really like your basic infrastructure services. We also have the first version of the plant cloud where the idea is that there's a lot of payloads that require you to have a very low latency loop, and you don't want to take a dependency on an internet connection that might be slower or not as reliable as you need it for a shop floor scenario. For that, we're deploying AWS Outposts in a plant. We actually have the first rack deployed, and we're looking at having use cases that require this low latency, use the Outpost compute resources, and also start moving some of the edge gateways to Outpost. So this gives us significantly more compute power and simplifies the management because you can deploy these racks, they're fully serviced, and we can scale more easily that way. There's also a lot of on-premise applications in the plants today that you can then move to a more modern infrastructure, reducing the complexity of these environments that you have today. The main part of the services we build is something that we coined the enterprise cloud. This is your standard off-the-shelf AWS with a few additional services and added bells and whistles. So the work we did when we talked earlier about provisioning these landing zones was required because a company like Volkswagen, it is complex. Like you have a lot of complexity in your network. You have a lot of different teams that have different interests. You have a lot of requirements into how you have to actually operate. There's a lot of compliance requirements, security requirements. So you want to make sure that by default, everybody does the right thing. So we automated this landing zone provisioning. There's a self-service application for a developer to just come in and ask for an account. We're managing these accounts through this application and then have blueprints of applications that work well with the setup that we start you with. So in this case, we actually sat down with Uwe's team in Dresden and started learning, like, what does this application look like? And how can we make it easier to build these applications? And how can we build operational and security best practices into the application in order for developers to actually make the getting something to production a lot easier. So for that, we're using services such as CloudFormation, we're using services such as Code Deploy, we're basically packaging the entire application up, and in this case, the first architecture we chose was a more modern architecture using AWS Lambda, using the API gateway, services like Cognito that actually help us with the authentication of users into the application. But then also integration with services like CloudWatch Logs, CloudWatch Metrics, like really everything you need to actually build a fully operational application. So developers can come in, they get an account, they take the blueprint, and they can start building. Data being today very heavily in AWS SiteWise, the developers can then come in and actually access the data directly. So they get to take the benefits of the platform pieces that are already there. If you already have data available, you already have services available, it's easier to get those integrated by doing this natively in the AWS ecosystem. The main services we're using today is, as we said, AWS SiteWise. We're also using IoT Analytics for a variety of use cases today. We're using IoT Core for data ingestion in some of the use cases. And then things like S3, lake formation to do the data lake management in the backend for some of the more complex use cases that require in-depth data analytics and then machine learning use cases as well using Amazon SageMaker. This is really the very first iteration of what we have. I can guarantee you if we give a talk in a year from now, this is going to look very different and probably not going to fit on one slide. This relatively simple architecture really was purely dictated by a few use cases that we did this year. There's a lot of learnings that came with it. We actually had an architecture we discussed at the beginning before we got going, and it looked a lot different than this. One thing I also want to be clear about is this is not a cloud-only system. Like you will not be able to build something like this cloud only just because of the physical aspect that your machines are at the shop floor. You need ways to manage your data. You need ways to get the data out. You need ways to process the data, to pre-aggregate it. There's a lot of on-premise systems, like Uwe was saying, a lot of data is in SAP. There's MES systems, there's SCADA systems. You actually need access to all that data and make it available in the cloud. But to do that, there's a lot more to it than just, unfortunately, at this point, than just clicking a button and having it available. So our focus over the next years where we're doing this is really going to be about how can we make all this data available in a consistent fashion and then make it easier for developers to really build the applications and not have to worry about the plumbing that you need to do this safely and at scale. With that. We're going to move to questions, if there are any. Wie zu den ganzen Chefs davon überzeugt, das zu tun.
Yes. So I'm only in the execution of this platform, so I don't do any suggestions with this. But I think Frank can do here some explanation, if you want, on the strategic approach. We have to decided on AWS or so. I build only the things with my team. So
maybe to summarize it at a high level, there has been like Amazon and a lot of other companies. They talk a lot. Our executives talk a lot, and Volkswagen is on a huge transformation in multiple dimensions. So there's a lot of chat about what is going on there. And the way that this whole collaboration was started is at the higher levels of both companies, where there's a business problem and there's an opportunity. And by partnering, we hopefully help Volkswagen to move faster on optimizing production. And at the same time, we learn a ton. Like we've now been doing this for a bit more than half a year. There's been a long list of features and products that AWS already has, and there's a long list of product ideas that is coming out of this collaboration. There's a lot of learnings on both sides. So I think getting the general management motivated and the higher levels in your company was really mostly driven by there's mutual benefits for everybody here. And if we move jointly, we both move a lot faster.
Yes, you have seen the MVP at first here. We have not such the software not in place at the moment. So we want to deliver the software on the end of the year or in Q1 in 2020. But we hope that we increase the productivity by the actual data, because now we have the data on the Morgenrunde. It is from 8 till 9, the shop floor managers talk together and improve the process on this data point. And we hope with when we have the data stream over the day, so we can do something within the day and not day by day. So I hope through the transparency, I think we can improve a lot. Furthermore, we have the loss recognition. So we write it. We collect reasons for the problems in the system now, and so we have an Pareto analysis over our failures, and so I think it will improve by a very easy way.
I think the main way, at least from our view as well, there's a lot of processes that today the visibility into the details of the process is relatively limited. So even by making data available, like we have various use cases, and one other one in a different plant actually. The team there works on the same machine for probably 20 years, at least, if probably more. There were a few insights we could get, and I don't want to go into the detail of the use case in this case, but those insights to people that were running the machine for 20 years, they could almost not believe when they saw them the first time. So with correlative analysis and a few other things, the insights you can get by combining getting the machine data, making it available, and combining it with more modern techniques from like statistics and machine learning is very, very powerful. And not just in building like an application that gives you the visual insight, but at actually figuring out what truly matters in your process, because people optimize over time, and they do really, really well. But the correlation when you have a lot of different data points is not something that a person can easily do, especially if the data points are in the hundreds of different data points. Yep. So the key piece is really latency. There's various use cases where you want to have the compute as close to your shop floor as you possibly can. Like we're physically, I guess, about 200 meters from where the outpost rack runs to the actual shop floor with a fiber run and very few switches in between. So it makes a difference that if you would go from Wolfsburg, which is in northeastern Germany, all the way to Dublin or to Frankfurt, it's still several hundred kilometers to Frankfurt from there. The latency is going to be larger than if you just have it on your shop floor. So the other one is that there's some machines where the amount of data that you generate are the very accurate term, humongous. So processing this in the cloud in many cases is not easily feasible because the amount of bandwidth we would need to stream this data continually would exceed what we have available right now. So being able to do data aggregation, for example, on Outpost and things like local inference on a rack that is physically in your data center is much easier to do that, especially with machines that produce large amounts of data. So things like predictive maintenance use cases, for instance. The amounts of data you have to do for your training or for your pre-aggregation are pretty significant. So it's just easier if you do it that way. So we started out, so we will, yes. We started out in one region. We only work with a select amount of plants to get started. We're now, next year is really focused on scaling this out to more plants. At the moment, all those plants are in relative close proximity in Europe. So we run in EU West, in that case, EU West 1. So, as Uwe already said, we're at the point now where we have the use cases in MVP, like where we have them working, and we're now working on getting them in front of the internal customers. So we don't yet have data on how much we captured. On the second one, the scope of what we're looking at is really everything in logistics and production. It's like whatever impacts the production effectiveness in the largest way we work on. Like we're trying to maximize the value here, and if this is in the end a application that helps us track logistics or optimize supply chain, or if it is something that helps us optimize a production process at the shop floor, it's open. We just happen to start with use cases in the plants. We also have some work with the logistics folks, but the one we picked here was on the machine side. Like the architecture would obviously look very different in that case because it's a very different purpose, but it is an end-to-end.
And in addition, today we work on the connectivity mostly. So we have to enable the platform to get the data in, and then we hope with normal tools for transparency to achieve, more increase the performance. Because the rocket science for data model, ML or artificial intelligence, I think this is the next step. At first, I think it will help our guys in the production that they see what has happened. And so we try to become more transparency on the shop floor. And so I think we can, through this update data, so we can, the problem solving is will be very good at in the future. So I think transparency is the first connectivity, transparency, and I think the other complex algorithms will come later.
It's also a matter of getting buy-in. Like we're just starting out. Volkswagen is a huge company, and getting people on board and actually getting people to see the value of what you do. You really want to have something in front of people very quickly, so they actually see that this is actually happening. And I think at that we're succeeding at this point.
But there are also use cases like computer vision, at the time and place. So we want to increase the quality, or we want to reduce the effort for quality control, quality control. So it will help at the moment now to avoid that we have the wrong labels for the Chinese market. So the car come back if you have the wrong labels on the car. So it's a little use case, but it had a, yes, an increase.
It's a very small cause,
yes,
relatively easy to solve, very large commercial impact.
yes, commercial.
Yes. So at different places actually. So we're working with Siemens when it comes to the machine connectivity. So we showed we didn't go into what hardware exactly is underneath a lot of this. So Siemens has a variety of PLCs that directly offer OPC UA connectivity, for example. They have a variety of edge gateways and edge compute capacity, as well as edge software ecosystem that is being used in here.
Mm-hmm.
In the fullness of time, it'll be a mix. When you look at the use cases, it's always a bit of a balance. You can move a lot faster when you just have things in the cloud. There's no compute capacity I need. It gives us the capability to build things very quickly. That being said, with Outpost, those are exactly the use cases. You have EMR support on Outpost. There's more products coming to Outpost over time, like they were presenting yesterday as well. It starts giving us a lot more of these capabilities within the plant to actually do some of the analytics. Inference is another big use case where when it comes to doing your predictions on a machine learning model, in a lot of cases you rely on a fairly low latency prediction there. Doing this on-prem on a machine that is in your data center is going to be a lot quicker. So it will be more of a blend, but this was what we got started with, which also was the quickest way, to be honest, to get set up. The amounts of data also in this use case are not that large, so the analytics that have to happen are not as heavyweight. So there's different stages when you look at the connectivity that has to be working when you look at it in an end-to-end fashion. So you have the OT/IT connectivity, like the gateway that is directly interfacing with your machine, where, yes, most of the field bus protocols, actually a lot of them, you have to be an active component on the field bus, so you kind of have your heartbeat system built in that case. When you look at the next step, when you go from the OT/IT gateway to the edge gateway, those are usually fairly standard IT protocols, and we actually start having monitoring capabilities such as CloudWatch logs and CloudWatch metrics in place there. When you then start looking from the gateway to the cloud, you again have the same system there. So you don't have a traditional heartbeat monitor in that sense where you would actively send heartbeats all the time. Most of the time you have a fairly continuous stream of data, so you can actually also monitor an absence of data in a lot of cases. Machines being turned off is also a very fun problem where we can have a sidebar chat here, because it turns out that you need to shut down a plant from time to time to actually upgrade everything in there. When things go down, you should probably not report an operational effectiveness of 0. But you need to start accounting for these things as well, which is a lot of the problems that the SFM Plus solved by doing shift calendars and all that as well. All right, one more, and then I think we'll be around here and happy to answer more questions there as well.
You present an architecture that allows you to capture machine data and move them from your production plants to the cloud, right? But in one of your slides, I noticed that you have lots of lights in
So the slide we had at the beginning is basically a what are we setting out to do? So today we're still focusing on the machine-centric use cases. The additional data sources we have was mostly on-premise systems or existing systems at Volkswagen that we interface with that are outside of the machine data. So things like SAP being one key piece there, and then SCADA systems and a few others. All right, thanks a lot.
Thank you.
Thank you, everybody. Thank you, Uwe.